Right now, in the walls around you, electricity is moving. It travels through copper wire, no thicker than a pencil. It moves at nearly the speed of light, and the current reaching you at this moment may have begun its journey a long way from here, sometimes hundreds of kilometers away, at a power station you will never see, built by people whose names you will never know. You don't need to think about it. That's rather the point. The electrical grid is, by most measures, the largest machine ever built by human beings. It spans continents. It links together millions of individual devices, generators, transformers, substations, and wires, into a single continuous system. And it operates without pause. There is no moment when the grid switches off, catches its breath, and starts again. It has been running, in most of the developed world, for well over a century, without stopping. This is not a story about disaster. It's not a story about things going wrong. It's a story about something that mostly, quietly, goes right. A system so reliable that most people never think about it at all, until occasionally, for a few minutes, they do. Over the next few hours, we're going to trace this system from its beginning. We'll start in a small laboratory in London in 1831, where a self-taught scientist noticed something strange happening in a coil of wire. We'll follow two very different men, one relentlessly practical, one strikingly visionary, through the most consequential engineering argument of the 19th century. And we'll arrive, eventually, at the modern grid. A system of such complexity that it manages every single second to keep itself in a state of near perfect balance. You don't need to remember any of this. You don't need to follow every detail. Let the story move past you the way the current moves through the wires above you, quietly, continuously, without needing your attention to keep working. Let's begin. Michael Faraday was born in 1791 in a place called Newington Butts on the edge of London. His father was a blacksmith. The family did not have money for his education, and so at the age of 13, Faraday was apprenticed to a bookbinder. It turned out to be, in its own way, a kind of education after all. Working in the bookshop, surrounded by books he was meant only to bind, Faraday read them instead. He read whatever came through the door. And in 1812, a customer gave him tickets to attend a series of lectures at the Royal Institution in London, delivered by a chemist named Humphrey Davy. Faraday attended. He took careful notes. Afterward, he bound those notes into a book of several hundred pages and sent them to Davy, along with a request for work. Davy eventually hired him as a laboratory assistant. By 1831, nearly 2 decades later, Faraday was running his own experiments, and one of them involved coils of wire and magnets. He noticed something that, on the surface, seems almost too simple to matter. When he moved a magnet near a coil of wire, a small current flowed through the wire. Not constantly, only while the magnet was moving. When the magnet was still, nothing happened. When it moved, a current appeared. He called this electromagnetic induction, and it is, quite genuinely, the principle behind almost every generator that has ever produced electricity. The key detail, the one worth letting settle for a moment, is that motion is required. A stationary magnet does nothing at all. It is the changing of a magnetic field near a wire that produces a current. Faraday built a simple device to demonstrate this. A copper disc spinning between the poles of a horseshoe magnet. As the disc turned, a tiny current flowed continuously from its edge. It wasn't much. It wouldn't have powered a single lamp. But the principle was now established, sitting quietly in a London laboratory, waiting for someone to scale it up. Decades later, a Scottish physicist named James Clerk Maxwell took Faraday's observations and the observations of several other scientists working on electricity and magnetism, and expressed them as a set of mathematical equations. He published them in 1865 under the title A Dynamical Theory of the Electromagnetic Field. Those equations are still taught today. They still describe, with complete accuracy, the behavior of every generator, every transformer, and every motor on the modern grid. It began with a spinning copper disc, and a man who read books he wasn't supposed to. Through the 1850s and 1860s, engineers across Europe took Faraday's discovery and began, slowly, to make it useful. The device they built was called a dynamo. Its principle was exactly what Faraday had shown decades earlier, simply made larger and more deliberate. Spin a coil of wire inside a magnetic field, or spin a magnet inside a coil of wire, which achieves the same result, and a current flows continuously. The faster the spin, the stronger the current produced. Of course, something has to do the spinning. In these early machines, that something was usually a steam engine, a device already well understood by the 1860s, having powered factories and railways for decades. Steam turned a shaft. The shaft turned the coil. The coil, moving through its magnetic field, produced a current. Later, water would do the same job. A river or a waterfall turning a wheel, the wheel turning a shaft, the shaft turning the coil. The mechanical source changed. The electrical principle underneath it never did. By the 1870s, a Belgian engineer named Zenobe Gramme had developed a dynamo reliable and efficient enough to be used commercially. Gramme's design arranged its coils around a ring-shaped core, an arrangement that produced a far steadier, smoother current than the machines that came before it. Earlier, dynamos tended to produce a current that surged and dipped as the coil rotated, rather than flowing evenly. For the first time, electricity could be generated continuously, in useful quantities, and put to practical work, running arc lamps, for instance, in the streets of a few pioneering cities. Paris, in particular, embraced this early lighting enthusiastically, and for a time, visitors spoke of certain boulevards glowing with a light unlike anything they had seen before, harsh and blue-white against the gas lamps of every other street in the world. What was still missing, though, was a system. A way of taking electricity from the place where it was made and delivering it reliably to the places where people actually needed it. Their workshops, their streets, eventually their homes. That problem, the problem of distribution, would consume the next 2 decades of engineering effort, and it would produce one of the most consequential rivalries in the history of technology. Thomas Alva Edison was born on the 11th of February, 1847, in the small town of Milan, Ohio. Like Faraday, he had little formal education. Much of what he knew, he taught himself. By his early 30s, he was already one of the most famous inventors in America, known for the phonograph and for significant improvements to the telegraph. What made Edison different from most inventors of his era wasn't simply his creativity. It was his approach to invention itself, as something that could be organized, industrialized, produced on a schedule, the way a factory produces goods. In 1876, he established a laboratory at Menlo Park in New Jersey. It was, in a real sense, the world's first organized research and development facility. Edison himself described it, with characteristic bluntness, as a machine for producing inventions. He turned his attention to electrical lighting in 1878. At the time, the only widely used form of electric light was the arc lamp, extremely bright, harsh, and short-lived, suitable for lighthouses, suitable for street corners, entirely unsuitable for a sitting room. What Edison wanted was something gentler, something that could glow softly for hours at a time and be turned on and off as easily as a gas lamp. His team tested thousands of materials, searching for a filament that could glow without immediately burning out. Eventually, they found that a carbonized strand of bamboo could sustain a glow for well over 1,000 hours. On the 21st of December, 1879, Edison demonstrated the practical incandescent lamp publicly at Menlo Park. Thousands of people traveled to see it. But Edison understood something important, standing there among the glowing bulbs. A light bulb, on its own, was a curiosity. What he needed to sell wasn't the bulb. It was the electricity to power it. Edison's vision, from the very beginning, was a complete system. A central station generating electricity, cables running underground, carrying that electricity to homes and businesses nearby. He modeled the whole idea, quite consciously, on the gas-lighting networks that already threaded beneath the streets of American cities. He chose Lower Manhattan for the first installation, a dense, wealthy district that could support the considerable cost of the new technology. At 257 Pearl Street, he converted a building into a generating station, installing 6 enormous dynamos that his engineers nicknamed the Jumbos, each one driven by its own steam engine. On the 4th of September, 1882, Edison was present as the Pearl Street station was switched on for the first time. 82 customers, within about a mile of the station, received electrical power. 400 lamps lit at once. The system ran on direct current, what we call DC. In direct current, electrons flow steadily in a single direction, the way water flows through a pipe. Edison chose it because it was well understood, dependable, and compatible with the motors and lamps his laboratory had already developed. The business grew quickly. By the end of that first year, Pearl Street was serving several hundred customers. Edison built more stations in other cities. For a while, the model seemed entirely sound. But there was a limitation built into the physics of the system, one that Edison either didn't fully appreciate at first, or chose, for a time, not to dwell on. That limitation was distance. In a direct current system, voltage cannot easily be changed once electricity has been generated. Pearl Street's dynamos produced electricity at around 110 volts, and it had to be delivered at very nearly that same voltage. And copper wire, however good a conductor it is, still has resistance. Some of the electrical energy traveling through it is lost as heat. The farther the electricity travels, the more of it is wasted. Edison's system worked beautifully within about a mile of its generating station. Beyond that mile, it simply stopped working. His proposed solution was more stations, a dense scattering of small power plants across a city, each one serving its own small radius. It was, in its way, an elegant vision of decentralized power. It was also, in practice, extraordinarily expensive to build at scale. To understand why distance mattered so much, it helps to sit with the underlying physics for a moment. The power lost to resistance in a wire is proportional to the square of the current flowing through it. This means that doubling the current doesn't simply double the losses, it quadruples them. It's a relationship first described by the physicist James Prescott Joule, and it has a very practical consequence. If you want to send electricity a long distance without losing most of it as heat, you want low current and high voltage. Raise the voltage tenfold, and for the same amount of power, the current drops tenfold. And because losses scale with the square of current, those resistive losses fall not by 10 times, but by 100 times. The difficulty in the 1880s was that no practical device existed to raise or lower the voltage of direct current. Transforming DC from one voltage to another was, for all meaningful purposes, impossible with the technology of the day. And the device that could do this effortlessly, the transformer, works only with alternating current. Its steady, unchanging nature is precisely what makes direct current so resistant to transformation. Edison's entire system, then, was trapped at low voltage. Each station could serve only its own small neighborhood. Long-distance transmission, the kind that might allow a single large power plant to serve an entire city or an entire region, remained, for direct current, essentially unsolved. It's worth sitting for a moment with just how constraining this really was. A single Edison-style station, even a large one, might comfortably light a few thousand homes within its narrow mile-wide radius. But a growing American city in the 1880s might need to serve tens of thousands of homes, spread across an area many miles wide. To cover such a city with Edison's model would have meant building and maintaining dozens of separate power stations, each with its own boilers, its own engineers, its own fuel deliveries arriving daily by cart. It was not simply inefficient. At a certain scale, it became almost unworkable. Into that gap stepped two men whose names would become permanently and rather unfairly simplified, linked to the alternative. Nikola Tesla was born on the 10th of July, 1856, in the small village of Smiljan, at the time part of the Austrian Empire and today part of Croatia. His father was an Orthodox priest. His mother, by his own account many years later, possessed a remarkable mechanical aptitude and an extraordinary memory, qualities he believed he had inherited from her. Tesla studied physics and engineering, first at the Graz University of Technology in Austria, later at the Charles Ferdinand University in Prague. He was, by every account, an exceptionally gifted student, though he never completed a formal degree. In 1882, while walking through a park in Budapest with a friend, Tesla later described having a sudden and complete mental image: a rotating magnetic field and a motor that could use it without the troublesome brushes and mechanical contacts that plagued the direct current motors of the time. He is said to have sketched the idea in the dirt with a stick, right there in the park. For the next 2 years, he worked for Edison's telephone company in Paris, helping to install electrical systems across Europe. Then, in 1884, he sailed for New York, arriving, as the story is usually told, with 4 cents in his pocket and a letter of introduction addressed to Thomas Edison himself. Tesla worked briefly for Edison's operation in Manhattan through late 1884 and early 1885. The precise nature of their working relationship has, over the years, been simplified considerably in retellings that favor drama over documentation. What can be said with confidence is that they were, fundamentally, very different men. Edison was empirical, commercially minded, focused on incremental improvement. Tesla was theoretical, visionary, focused on elegant, complete solutions. By early 1885, they had parted ways. There followed a difficult period for Tesla. By some accounts, he spent time doing manual labor, digging ditches, after a group of investors failed to follow through on their financial commitments to him. But in 1887, he found new backing and opened his own laboratory on Liberty Street in Manhattan. There, over the following months, he developed a complete system: generators, transformers, and motors, all designed to work together using alternating current. Central to this system was the induction motor, and it's worth understanding, gently, why it mattered so much. Earlier electric motors, running on direct current, required something called a commutator, a mechanical switch made of copper segments and carbon brushes that had to reverse the current's path many times each second in order to keep a rotor spinning. Brushes wore down. Sparks jumped across the contacts. Maintenance was constant. Tesla's induction motor needed none of this. By feeding alternating current through multiple separate coils, arranged carefully around a stationary housing, he could create a magnetic field that appeared, to a simple conductive rotor placed at its center, to be rotating smoothly on its own, even though nothing in the motor's housing was moving at all. The rotor, quite naturally, followed this rotating field, turning in sympathy with it. No brushes, no sparks, no commutator to wear down, just 2 pieces of metal, one fixed and one turning, and a rotating magnetic field passing quietly between them. In May of 1888, he presented his Polyphase AC system to the American Institute of Electrical Engineers. Among those listening closely was an associate of a very different kind of businessman, a man named George Westinghouse. George Westinghouse was born in 1846 in Central Bridge, New York. Before electricity ever entered his thinking, he had already transformed the safety of railway travel, inventing the air brake, a system using compressed air to allow a single train driver to apply brakes to every carriage simultaneously, and the automatic railway signal, which helped prevent collisions between trains. Westinghouse was not, primarily, an electrical engineer, but he was an outstanding engineer in a broader sense, and a careful, patient businessman. And he had been watching the slow development of alternating current systems with considerable interest. A transformer-based system had already been demonstrated in Europe, in Gans, in Hungary, by 3 engineers named Zipanowski, Blathy, and Dairy. In 1885, Westinghouse purchased the American rights to their transformer designs and began building his own alternating current distribution system. What he lacked was an efficient AC motor. Tesla, as it happened, had one. In 1888, Westinghouse visited Tesla's laboratory. He purchased Tesla's Polyphase patents outright for $60,000 and agreed to pay a royalty of $2.50 for every horsepower of electrical capacity sold using Tesla's designs. It was, for the time, a remarkably generous arrangement. Westinghouse now possessed the complete system: transformers to raise voltage for transmission and lower it again for safe use, and Tesla's induction motor to turn alternating current back into useful mechanical work. The very thing direct current motors had always done, but without the mechanical wear and complexity that had limited DC. The confrontation with Edison was no longer avoidable. Before we follow the 2 systems into direct competition, it's worth pausing to understand, gently, what actually makes alternating current different, and why that difference mattered so profoundly. In an alternating current system, the direction of the current reverses repeatedly. In the systems that exist today, this happens either 50 or 60 times every second, depending on where in the world you happen to be. This reversal isn't an accident or an inconvenience. It arises naturally from the physical act of generation. As a coil of wire rotates inside a magnetic field, it passes first through one orientation, then, half a turn later, through the opposite orientation. The current it produces rises, reaches a peak, falls back to 0, reverses direction, reaches an opposite peak, and returns to 0 again. The cycle repeats, over and over continuously. The crucial advantage this creates lies in the transformer. Because the current in an AC system is always changing, it produces a magnetic field in a transformer's primary coil that is also always changing. And a changing magnetic field, as Faraday discovered all those decades earlier, induces a voltage in any nearby coil. The ratio of turns of wire between the 2 coils determines the ratio between the 2 voltages. More turns on the outgoing side, and voltage steps up. Fewer turns, and voltage steps down. A transformer, remarkably, has no moving parts at all. It is silent. It requires very little maintenance. And it means that electricity generated at, say, 10,000 volts can be stepped up to 100,000 volts or more for efficient transmission across long distances, and then stepped back down safely to 240 volts or 120 for use inside a home. This one capability, the quiet, effortless transformation of voltage, is what direct current in the 1880s simply could not offer. It is, in the end, the whole reason alternating current became the standard for the entire world. Edison's response to the rise of alternating current was not, in the main, a technical one. There is reason to believe that Edison understood, even at the time, that the underlying physics ultimately favored AC for transmission over any meaningful distance. His response, instead, took the form of a public campaign. He argued that alternating current was dangerous. Its higher voltages, necessary precisely for its efficiency over distance, were, he pointed out, genuinely more lethal if a line broke or a person came into accidental contact with the system. Direct current, running at a mere 110 volts, was, in his telling, far safer for use inside a home. He was not entirely wrong about the danger. High-voltage alternating current is, in a direct and immediate sense, more dangerous than low-voltage direct current. But the argument, as presented, rather obscured the larger technical and economic picture. In 1888, an electrical engineer named Harold Brown, working with what appears to have been quiet support and resources from Edison's own laboratory, began staging public demonstrations of AC's dangers. He electrocuted dogs and other animals in front of audiences, using alternating current supplied by Westinghouse equipment. These demonstrations were widely reported in the newspapers of the day. Brown was also involved in the development of the electric chair, which New York State adopted in 1888 as a supposedly more humane method of capital punishment than hanging. Part of the intent, it seems reasonably clear, was to link alternating current in the public imagination with death itself. Westinghouse's name did not appear anywhere on the apparatus, but the power source did. On the 6th of August, 1890, a man named William Kemmler became the first person executed by electric chair at Auburn Prison in New York. Westinghouse, who had tried through legal means to prevent the execution from taking place, later described the proceedings as botched, and he was not incorrect. The first application of current failed to bring about immediate death, and a second application was required. For a brief period, the phrase "to be Westinghoused" entered the language as a grim synonym for electrocution. It did not, in the end, change the underlying physics of the situation at all. There is something worth sitting with in this episode, quietly, as the story moves on. Edison was, by every measure, a genuine and prolific inventor, responsible for real and lasting contributions to the modern world. And yet, faced with a competing technology he could not out-engineer, his response was not to concede the point gracefully, but to wage what amounted to a fear campaign, using demonstrations designed less to inform the public than to frighten it. It's a reminder that the history of great inventions is very rarely a clean, tidy story of pure ideas competing on their merits alone. Business interests, public perception, and simple stubbornness all played their part, exactly as they still do today. The decisive public demonstration of the two systems came at the World's Columbian Exposition, held in Chicago in 1893, an event marking the 400th anniversary of Columbus's arrival in the Americas, and one of the largest public gatherings America had seen up to that time. The contract to light the entire exposition, its 200 buildings, and its extensive grounds, was put out for competitive bidding. General Electric, which had by then absorbed Edison's original company, bid approximately $554,000 to supply direct current lighting throughout the fair. Westinghouse bid roughly $399,000 to supply alternating current instead. Westinghouse won the contract. Over the course of the exposition, from May through October of 1893, more than 27 million visitors experienced electrical lighting on a scale most of them had never witnessed. 100,000 incandescent lamps illuminated the grounds each evening. For a great many visitors, it was their very first encounter with electric light of any kind. The effect on public opinion was considerable. Alternating current was no longer an abstract danger discussed in newspaper columns. It was light. It was order. It was, quite simply, beautiful. Westinghouse and Tesla had shown the country what their system could do. The final chapter of the War of Currents was written, fittingly, at Niagara Falls. Since 1889, a consortium of investors had been developing plans to harness the immense natural power of the falls and transmit the resulting electricity to the city of Buffalo, some 35 kilometers away. After careful deliberation, including consultation with both Edison and Westinghouse, the Niagara Falls Power Company awarded the generating contract to Westinghouse in 1893. The Edward Dean Adams Power Station, known simply as Station Number 1, was built on the American side of the falls. It housed 3 of Tesla's Polyphase generators, each capable of producing 5,000 horsepower at a voltage of 2,200 volts. On the 16th of November, 1896, electrical power generated at Niagara Falls reached Buffalo, 35 kilometers away. The longest practical transmission of electrical power achieved in North America to that point. Tesla later wrote that, standing near the falls, hearing the machinery he had once imagined walking through a Budapest park, now humming quietly beneath tons of falling water, was among the most moving experiences of his life. By the turn of the century, the argument, in any meaningful sense, was over. Alternating current had won. The technical and economic logic was, by then, simply too clear to argue against. Edison's direct current system, remarkable as it had been in its moment, could not scale to power a modern nation. Alternating current could. With the technical argument settled, a quieter question remained. Alternating current could, in principle, serve an entire city or an entire region. But someone had to decide how such a system would actually be organized, financed, and sold. That person, more than any other, was a man named Samuel Insull, Insull had come to America from London in 1881, initially working as a personal secretary to Thomas Edison himself. He was present for much of Edison's early work, including the Pearl Street project. But it was later, after Insull moved to Chicago to run the Chicago Edison Company, that he made his most lasting contribution. Not a piece of hardware, but an idea about how electricity should be sold. Early electrical utilities, in the main, charged a flat rate, or charged based on the number of lamps or devices a customer owned. Insull recognized a deeper truth about the economics of a power station. The enormous cost of building a generating plant was largely fixed, whether it served 10 customers or 10,000. The more customers a station could serve, and the more evenly their demand was spread across the day, the cheaper electricity became for everyone. From this insight, Insull developed the metered rate, charging customers based on their actual measured consumption, tracked by the electricity meter, a device that itself became a quiet fixture of nearly every home in the developed world. He also pursued something that seemed, to some contemporaries, almost counterintuitive. He pushed to expand service into poorer neighborhoods and into outlying areas, on the reasoning that more customers, even lower-paying ones, made the whole system more efficient and therefore cheaper for all. Insull's approach, whatever its later complications, his utility holding company empire would collapse dramatically during the Great Depression, established the basic commercial model that electricity utilities across the world would follow for the next century. Electricity was no longer to be a luxury reserved for the wealthy few who lived close enough to a generating station. It was to be sold, metered, and delivered as a universal service. For all the elegance of Insull's model, one problem remained stubbornly unsolved into the early decades of the 20th century. Electricity had come to cities. It had not yet come in any meaningful way to the countryside. The economics were simple and unforgiving. Running power lines to a farmhouse several kilometers from the nearest town cost the same, more or less, whether that farmhouse used a great deal of electricity or very little. Private utility companies, operating for profit, saw little reason to extend lines across sparsely populated land to serve a handful of distant customers. By the early 1930s, in the United States, fewer than 1 in 10 farms had access to electricity at all. Most rural households still lit their homes with kerosene, much as they had for generations. In Britain, the problem was addressed nationally, and early through the very same Electricity Supply Act of 1926 that had already resolved the AC transmission question. The Act created the Central Electricity Board, tasked with linking the country's most efficient power stations into a single, synchronized network, operating at 132,000 volts and 50 cycles per second. Construction proceeded steadily through the following years, and by 1933, the grid, Britain's first true national network, was substantially complete, its towers marching the length and breadth of the country, connecting some 122 power stations that had previously operated in isolation from one another. In the United States, the equivalent effort came somewhat later and took a different institutional form. In 1935, President Franklin Roosevelt established the Rural Electrification Administration by executive order, and Congress made it permanent the following year through the Rural Electrification Act of 1936. Rather than compelling private utilities to extend their networks, the administration offered low-interest loans to newly formed rural electric cooperatives, organizations owned collectively by the farmers and communities they served. These cooperatives strung their own lines, often through enormous volunteer effort, pole by pole, farmhouse by farmhouse. Across land, the private utilities had judged unprofitable. The effect over the following 2 decades was transformative and, in its way, quietly moving. Farms gained not just light in the evenings, but electric water pumps, milking machines, and refrigeration. Changes that reshaped rural life as thoroughly as any single technology of the century. By the early 1950s, the great majority of American farms had electricity, a figure that had stood below 10% barely 20 years before. What both stories share, the British and the American, is a recognition that arrived slowly, but arrived nonetheless. That a power grid, to fulfill its purpose, could not simply follow the shortest path to the largest profit. It had, eventually, to follow people, wherever they happened to live. With alternating current established, the 20th century saw the steady, patient construction of what we now simply call the grid, an interconnected web of generation, transmission, and distribution infrastructure, running continuously across entire nations, and, in places, across entire continents. The journey electricity takes, from the moment it is generated to the moment it reaches a socket in a wall, passes through 3 distinct stages: generation, transmission, distribution. Each of these stages operates at a very different voltage from the others. At the power station itself, whether it burns coal or gas, or splits atoms, or turns a river, or catches the wind, generators typically produce electricity at what engineers call medium voltage, somewhere between 11,000 and 25,000 volts, depending on the design of the plant. This is, broadly, the voltage at which generators themselves operate most efficiently. Standing beside the power station is almost always a step-up transformer, one of the largest single objects in the entire electrical landscape. These transformers are often the size of a small house and can weigh several hundred tons. Their task is to raise the voltage quite dramatically for the journey ahead. In the United Kingdom, the highest voltage used for transmission is 400,000 volts. In parts of the United States, some lines run at 765,000 volts. In China, certain lines, built to move electricity across truly vast distances, operate at over 1 million volts. At voltages that high, the current flowing through the wire becomes, correspondingly, very small. And because resistive losses depend on the square of current, this small current means the electricity can travel hundreds of kilometers, losing only a modest fraction of its energy along the way, as gentle, barely perceptible heat. Not every power station on the grid is asked to do the same job, and this quiet division of labor is worth pausing on, because it shapes almost everything about how a modern grid is planned. Electricity demand is never constant. It rises through the morning as people wake and businesses open, dips slightly through the middle of the day, rises again into the early evening as households return home, cook and switch on lights and appliances, and then falls away slowly through the night toward a quiet early morning low. Overlaid on this daily rhythm are seasonal patterns too. Heating demand, climbing through winter evenings, cooling demand, climbing through summer afternoons. To meet this shifting pattern efficiently, grid planners have long relied on a rough division between two kinds of generation. Baseload power stations are large, efficient, and slow to start or stop. Traditionally, coal and nuclear plants, though increasingly in many grids, wind and solar contribute a growing share of this steady background supply. These plants run continuously, day and night, meeting the demand that never really disappears. The portion of consumption that exists even in the stillest hours before dawn. Peaking plants serve a different purpose entirely. These are typically smaller, faster-starting facilities, often gas turbines, not unlike jet engines mounted on the ground, capable of reaching full output within minutes rather than hours. They sit largely idle for much of the day and are called upon only during the sharp, short-lived surges in demand. A hot summer afternoon, when every air conditioner in a city switches on at once, or a cold winter evening when heating and lighting demand arrive together. The economics of this arrangement are, in their own way, elegant. Baseload plants are expensive to build, but cheap to run continuously. Peaking plants are comparatively cheap to build but expensive to run, since they burn more costly fuel for the small number of hours each year they're actually needed. Matching the right kind of generation to the right moment in the daily rhythm of demand is one of the quieter, more continuous acts of engineering judgment that keeps the grid both reliable and reasonably affordable. The transmission line is, in its way, one of the most familiar sights in the modern landscape. So familiar that it has become almost invisible. Steel towers, 40 or 50 meters tall, marching in long rows across open fields and low hills, carrying cables that catch the light and gleam faintly silver against the sky. The cables themselves are not, as many people assume, made of copper. For transmission lines, aluminium is the preferred material, lighter than copper, and nearly as good a conductor, which matters enormously when a cable must be suspended, unsupported, across long spans between towers. Strands of aluminium are wound around a central core of steel, which provides the tensile strength the aluminium alone would lack. The cables are bare. No insulation covers them at all. At the voltages used for transmission, the surrounding air itself provides sufficient insulation. What the towers must do is simply keep the cables separated from each other and from the ground by a distance wide enough to prevent the current from arcing across the gap. The porcelain or glass discs you may notice where a cable meets a tower are insulators, quietly performing exactly this function. Transmission lines carry current that reverses direction either 50 or 60 times each second. 50 in Europe, in Australia, and across most of Asia, 60 in North America, and in parts of Japan. These particular frequencies were settled upon in the earliest decades of electrical supply, largely for reasons of historical happenstance, and they have never changed since. In the United Kingdom, the transmission network, what is generally called the national grid, comprises something in the order of 7,000 kilometers of overhead line. In the United States, the equivalent network extends across more than 700,000 kilometers. At regular intervals along the transmission network sit grid substations, and here begins the slow, careful process of reducing voltage back down toward something usable. These substations are large, fenced compounds filled with transformers, circuit breakers, and switching equipment, humming quietly to themselves at all hours. Electricity arriving at transmission voltage is stepped down here to what is generally called primary distribution voltage, typically somewhere between 33,000 and 132,000 volts, depending on the country in question. From these primary substations, electricity moves onward, onto the distribution network proper, smaller pylons in rural areas, or underground cables, more often beneath city streets. These distribution lines feed further substations, smaller still, where the voltage is reduced once again. In the United Kingdom, the next stage typically brings voltage down to 11,000 volts. In the United States, distribution voltages commonly range somewhere between 4,000 and 35,000 volts. The final transformation happens very close to the point of use. Distribution transformers, sometimes cylindrical units mounted on wooden poles along a suburban street, sometimes green-painted metal boxes set discreetly into a pavement, reduce the voltage one last time to whatever level is delivered into homes and businesses, 230 volts. In the United Kingdom and in Australia, 120 volts across most of North America. By the time electricity reaches a socket in a wall, it has typically been transformed 3 or 4 separate times, stepped up at the generator, carried across great distances at very high voltage, and then patiently, in careful stages, brought back down to something safe and useful. And the entire journey, from generator to lamp, takes only a small fraction of a second. For most of the grid's history, the electricity meter, that quiet dial or spinning disc mounted on the side of a house or in a basement cupboard, was a purely mechanical device. Someone had to visit it periodically and read it by eye, copying down a number that would later appear on a bill. Over the past 2 decades, in many countries, that quiet, unassuming device has been replaced by something considerably more capable. The smart meter, as it's generally known, measures consumption not once a month or once a quarter, but continuously, often in intervals as short as 30 minutes, and communicates that information back to the utility automatically, without anyone needing to visit the property at all. This might seem, on its surface, a fairly modest convenience, an end to estimated bills, an end to the meter reader's periodic visit. But its real significance lies elsewhere, in how it changes the grid operator's view of the system as a whole. Where once a utility could only estimate, in a rough and generalized way, how demand was distributed across a city or a region, a network of smart meters offers something closer to a live, granular picture. Near real-time visibility into exactly where electricity is being used, and how that pattern shifts through each day. This visibility, paired with the broader monitoring and control systems that grid operators rely on, generally referred to as SCADA, an acronym for Supervisory Control and Data Acquisition, allows the kind of fine-grained balancing act described earlier in this recording to happen with considerably more precision. It also opens the door to new forms of flexibility. Time-of-use pricing, which encourages consumers to shift some of their usage away from the evening peak, or automated demand response, in which certain appliances, a hot water cylinder, an electric vehicle charger, can be instructed to pause briefly during moments of system stress, almost always without the person at home ever noticing. The grid, in other words, has slowly gained something like a nervous system, layered quietly on top of the physical infrastructure of wires, transformers, and generators, sensing in ever finer detail exactly how the balance between supply and demand is shifting moment to moment across an entire country. Scattered throughout the grid, inside substations, mounted along transmission towers, tucked into the base of distribution poles, sit devices whose entire purpose is to notice almost instantly when something has gone wrong, and to act before that fault can spread. These devices are called protective relays, and their logic, though it now runs on digital electronics, follows principles established more than a century ago. A relay watches a particular section of the grid continuously, measuring current, voltage, and, in some cases, the direction electricity happens to be flowing. When it detects a pattern outside of what's expected, a sudden surge of current, for instance, of the kind caused by a fallen tree branch touching a line, or by a fault deep within a piece of equipment, it sends an instruction within a matter of milliseconds to a nearby circuit breaker. A circuit breaker performs a task that sounds almost deceptively simple. It interrupts the flow of current, physically separating one part of the circuit from another. But interrupting a high-voltage current safely is a genuinely difficult engineering problem. At the moment contacts begin to separate, the current wants very much to keep flowing and can leap the widening gap as an arc, a small, extremely hot channel of ionized air. Modern circuit breakers are built specifically to extinguish this arc quickly and safely, often using pressurized gas, oil, or a vacuum chamber, depending on their design and the voltage involved. What makes this system so effective is its layered, almost nested design. A fault on a single distribution line, serving perhaps a few dozen homes, should ideally be isolated by the smallest, most local breaker available, protecting the rest of the network from ever noticing the disturbance at all. Only if that local protection fails does the fault escalate outward, tripping progressively larger breakers further up the system. It's a quiet hierarchy of defense, each layer designed to contain a problem before it reaches the next. This is, in fact, precisely the mechanism that worked as intended during the 2019 UK event described earlier. Automatic protection isolating a controlled, limited portion of demand in order to prevent a much larger and more damaging collapse. The grid, in this sense, is built not to prevent every fault from ever occurring. Faults on a network this vast are simply inevitable, but to contain each one so completely that most people never notice it happened at all. The alternating current flowing through the grid does so at a very precise frequency. In Europe, in Australia, and across most of the world, that frequency is exactly 50 cycles each second, 50 Hertz. In North America, it is exactly 60. These figures are not loose approximations. They are maintained at every moment with real precision. Why does this matter so much? Because the grid in any given region is not really a collection of separate power stations and separate customers. It behaves instead as a single, unified, synchronized system. Every generator connected to it rotates in near perfect step with every other generator on the same network. Across Europe, from Spain in the west to Poland in the east, every generator turns to the same 50-cycle rhythm. If a generator should ever fall out of that synchrony, it disconnects itself automatically, almost instantly. Reconnecting it to a grid it is no longer in step with would cause serious, immediate damage. The frequency of the grid at any given moment is really a direct reflection of the balance, or the imbalance, between how much electricity is being generated and how much is being consumed. When the two are perfectly matched, frequency holds steady, exactly where it should be. When demand outpaces supply, when more electricity is being drawn from the system than is being fed into it, the generators slow, almost imperceptibly, under the load, and frequency drifts slightly below its target. When supply exceeds demand, the opposite happens, and frequency drifts upward. Grid operators, organizations such as National Grid in the United Kingdom, AEMO in Australia, and various regional operators across North America, watch this frequency continuously, every second, without pause. Their task, at every moment, is to hold it within a narrow band, typically no more than half a hertz above or below its target. A deviation larger than that triggers automatic protective measures across the system. The tools available to maintain this balance include what's called spinning reserve. Power stations kept running, but below their full output, ready to increase generation within seconds if called upon. They also include demand-side response, in which large industrial customers agree, in advance, to reduce their own consumption at moments when the grid comes under particular strain. The electricity grids of the developed world are not, in truth, single unified networks stretching seamlessly from one end of a continent to the other. They are, instead, collections of interconnected systems, managed by many different operators, often spanning the borders of several countries at once. In Europe, the synchronous grid, coordinated by an association called ENTSOE, links together the electrical networks of some 35 countries, from Portugal in the far west to Ukraine in the east. All of them share the same 50 Hertz frequency. A power station generating electricity in Germany is, in a real and continuous sense, electrically connected to to a substation in Romania. In North America, there are 3 largely separate interconnections: the Eastern Interconnection, the Western Interconnection, and the Texas Interconnection, managed by an organization called ERCOT. Texas's grid is deliberately kept isolated from its neighboring systems, a decision rooted in regulatory choices made in the early decades of the 20th century, and one that has, at times, had significant consequences during periods of extreme weather. This interconnection between grids provides real resilience. A sudden loss of generation in one region can often be offset by surplus power flowing in automatically from a neighboring region, along the transmission lines that connect them. But that same interconnection also means that failures, on rare occasions, can spread. The largest blackout in North American history occurred on the 14th of August, 2003. A software fault within an Ohio power company's control system, combined with unusually high demand, a series of transmission line failures, and some delay in the human response to those failures, triggered a cascade that, within a matter of minutes, cut power to some 55 million people across 8 American states and the Canadian province of Ontario. The investigation that followed was thorough, and its findings reshaped grid operating procedures across the whole of North America, adding redundancy, improving monitoring systems, and establishing clearer protocols for how operators should respond to early warning signs. The grid operating today is, by a considerable margin, more resilient than the one that failed in 2003. For most of the grid's history, the balance between supply and demand that we described earlier had to be managed almost entirely through generation. Spinning reserve held ready in idling power plants, ramped up or down within seconds or minutes as needed. There was, in effect, no way to store meaningful amounts of electricity at grid scale. It had to be generated at the moment it was used. That began to change in a quiet and rather dramatic way in South Australia. In September of 2016, a severe storm, one meteorologists described as a once-in-50-years event, damaged transmission infrastructure across the state and triggered a widespread, statewide blackout. In the aftermath, the South Australian government, together with the renewable energy developer Neoen and the American company Tesla, agreed to install what was, at the time, the largest lithium-ion battery installation in the world, positioned beside an existing wind farm near the town of Jamestown. Tesla completed the installation, remarkably, within 100 days. The Hornsdale Power Reserve, as it became known, began operation in December of 2017, with an initial capacity of 100 megawatts. It was later expanded in 2020 to 150 megawatts. What made it so significant wasn't simply its size, but its speed. A traditional gas power station, held in reserve, might take a matter of minutes to respond to a sudden loss of generation elsewhere on the grid. Hornsdale could respond within a fraction of a second. Faster, in fact, than the mechanical response of a spinning turbine, because there was no physical mass that needed to accelerate. the battery's power electronics could simply begin discharging instantly the moment a deviation in grid frequency was detected. Within its first 2 years of operation, Hornsdale was credited with saving South Australian electricity consumers well over $100 million, primarily by providing frequency response and reserve services more cheaply and more quickly than the gas-fired plants that had previously provided them. It also demonstrated something the industry had, until then, mostly treated as a theoretical possibility: that batteries could genuinely substitute for at least part of the role once played exclusively by large spinning generators. Grid-scale batteries have since been built across many countries, and their role has continued to expand, not only providing fast frequency response, but increasingly storing surplus solar generation from the middle of the day for use during the evening demand peak, smoothing out precisely the kind of variability that renewable generation introduces into a system built, originally, around the steady, predictable rhythm of burning fuel. If the events of 2003 taught the industry a great deal about the dangers of cascading failure across a large interconnected grid, a smaller, more contained incident in Britain, some 16 years later, offered a quieter but no less instructive lesson. On the afternoon of the 9th of August 2019, a lightning strike hit a high-voltage transmission line in eastern England. Lightning strikes on transmission lines are not, in themselves, especially unusual. Grids are engineered to withstand them routinely, and this particular strike caused no lasting damage to the line itself. What followed was more surprising. Within about a minute of the strike, 2 separate generators, entirely unconnected to one another, and each affected by the same electrical disturbance in different ways, reduced their output unexpectedly. The Hornsdale offshore wind farm off the Yorkshire coast lost a substantial portion of its output as its turbines' control systems responded unexpectedly to the voltage disturbance the lightning had caused. Almost simultaneously, a steam turbine at the Little Barford Gas Power Station in Bedfordshire tripped offline after its control system registered what its operator later described as an anomalous and ultimately erroneous reading from its speed sensors. The combined loss, close to 1,900 megawatts in total, was greater than the reserve the grid operator had prepared to cover on that particular afternoon. As frequency began to fall, automatic protection systems, the same kind of safeguard described earlier, designed to prevent a small disturbance from cascading into something much larger, disconnected a small proportion of total demand in a controlled and deliberate way in order to bring supply and demand back into balance. Around 1 million customers across parts of England and Wales lost power for a period of that afternoon, most for less than an hour. It was, by the standard of large-scale grid failures, a comparatively minor event, and one the system's own protective mechanisms handled largely as designed. But it offered a genuinely useful lesson that in a modern grid increasingly composed of many smaller, more varied sources of generation, a single external trigger, in this case one lightning strike, could still, through coincidence and complexity, cause 2 quite different systems to fail in the very same minute. The investigations that followed led to a series of changes in how wind farm control software responds to sudden voltage disturbances. A small but meaningful adjustment made to a system that, on the whole, continues to work. There is a quiet, rather elegant footnote to the whole story of the war of currents. Direct current, in a sense, has returned, not in the form Edison once imagined, small, local, limited in reach, but almost as its opposite. Very high voltage direct current, used now for bulk transmission across very long distances. Modern power electronics, using semiconductor devices with names like thyristors and IGBTs, can now convert alternating current into direct current, and back again, efficiently, even at extremely high voltages. This technology, known as high voltage direct current, or HVDC, was first used commercially in 1954 on a cable connecting mainland Sweden to the island of Gotland. HVDC offers certain genuine advantages over alternating current in particular circumstances. For very long distances, beyond roughly 600 kilometers, the lower resistive losses of direct current become the deciding factor. For undersea cables, direct current is strongly preferred because long alternating current cables tend to accumulate an unhelpful electrical charge along their length, and for connecting two grids that operate at different frequencies, or two grids that are, by deliberate design, kept unsynchronized, direct current offers a seamless link without requiring either system to change its rhythm. China now operates the highest voltage transmission lines anywhere in the world. HVDC connections running at plus or minus 1,100,000 volts, spanning over 3,000 kilometers, carrying electricity generated by hydroelectric dams in the west of the country to the cities of the east. Edison's direct current, transformed by more than a century of quiet technological refinement, now carries electricity across an entire continent. At each end of an HVDC line sits a converter station, a large industrial facility, quieter in appearance than a power station, but no less intricate, filled with tall banks of power electronics. At the sending end, one of these stations gently converts alternating current into direct current for its long journey. At the receiving end, an equivalent station converts it back again, restoring the familiar 50 or 60 cycle rhythm the surrounding grid expects. These converter stations are, in a sense, the quiet interpreters of the modern grid, allowing direct current, alternating current, and even grids running at entirely different frequencies to speak to one another without either side needing to change its own native rhythm. One of the more remarkable examples of this technology lies quietly beneath the North Sea, largely unseen and, for most people, entirely unknown. In October of 2021, an interconnector called the North Sea Link began operation, running some 720 kilometers beneath the seabed, from the village of Kvildal in southern Norway to the town of Blyth on the northeast coast of England. It is, at the time of this recording, the longest subsea power interconnector in the world. The purpose of the link is quietly elegant. Norway generates the great majority of its electricity from hydropower, drawing on vast mountain reservoirs that can be released or conserved with relative ease. Britain, by contrast, generates an increasing share of its electricity from offshore wind, abundant but variable and entirely dependent on the weather. The North Sea link allows the two systems to lean on one another. On a calm, windless day in Britain, Norwegian hydropower can flow west beneath the sea to fill the gap. On a windy day, when Britain's turbines are producing more than the country needs, that surplus can flow east instead, allowing Norway to hold back its own reservoirs, effectively storing British wind energy as water held gently behind a dam, ready to be released again whenever it's needed. At its full capacity, the link can carry 1,400 megawatts. Enough, broadly speaking, to power well over 1 million homes. The grid never rests. At this very moment, transformers are humming softly in substations in every city on Earth. Control room engineers are watching frequency displays, adjusting generation, quietly rerouting power around minor faults before most people ever notice them. Turbines are turning somewhere, in power stations burning coal or gas, or splitting atoms, or catching falling water, or turning slowly in the wind. The electrons moving through the wire in the wall beside you are not, in fact, the same electrons that left a power station somewhere far away. Electrons themselves move quite slowly through copper wire, a fraction of a millimeter each second. What actually travels close to the speed of light is the electrical field, the influence that pushes them gently along. The energy you use arrives almost instantly, carried not by the electrons themselves, but by a wave moving through the wire. Michael Faraday discovered the underlying principle in 1831, working with a copper disc and a horseshoe magnet. Edison lit a small part of Manhattan in 1882. Tesla and Westinghouse settled the long argument at Niagara Falls in 1896. And in the century and a quarter since then, the system they built has grown into something none of them could have fully imagined, and none of them alone could ever have managed. It powers hospitals. It powers phones. It is, quite possibly, powering the very device through which you are hearing these words. Consider for a moment everything that had to align for that to be true. A scientist's curiosity about a moving magnet in 1831. A bookbinder's apprentice who happened to read the books he was meant only to bind. A bitter, decades-long rivalry between two men who could not have been more different, and who, between them, without ever quite intending to, built the framework for a system neither could have managed alone. A Belgian engineer's dynamo, a Hungarian transformer, a Serbian visionary sketching in the dirt of a Budapest park, a Pittsburgh businessman with a talent for railway brakes, farmers in Ohio, and villagers in the Scottish Highlands, waiting years, sometimes decades, for a line finally to reach their door. Engineers in a control room in the 1930s, and engineers in a control room tonight, watching the very same trembling needle, holding the very same fragile, constant balance. None of them individually built the grid. It was built gradually by thousands of quiet decisions made across 2 centuries by people who mostly never met one another and who could not have imagined the full shape of what they were slowly assembling. And it runs on quietly in the walls around you and in the ground beneath the streets following the very same laws of physics that a self-taught bookbinder's apprentice first noticed, working with a copper disc in a small London laboratory nearly 200 years ago. Somewhere, right now, a substation stands quietly in the dark. Its transformers hum, low and even, a sound too constant to really be called a sound at all. Indicator lights glow faintly green and faintly amber, arranged in careful rows across a control panel that no one is currently watching. Far above, transmission lines cross a dark field, catching every so often a thin edge of moonlight. And somewhere beneath a hydroelectric dam, water moves through a turbine, cold and black and endlessly patient, turning a shaft that has been turning without pause for longer than most people have been alive. Somewhere else, a wind turbine turns slowly against a night sky, its blades catching almost nothing but starlight, the faintest whisper of moving air, the only sound for miles. Somewhere, a battery sits in a quiet steel enclosure, holding a small portion of an afternoon's sunlight, waiting patiently to release it gently into the coming evening. Somewhere, a control room engineer glances, without much urgency, at a dial that has not moved in hours, and looks away again, satisfied. The grid holds itself in balance. It has held itself in balance through wars and storms and the slow turning of an entire century. It held itself in balance last night while you were sleeping, and the night before that, and every night before that, stretching back further than anyone alive can quite remember. Somewhere, a lamp is switching off in a room much like this one, its warm light fading slowly into the dark, the current that fed it already moving on, already needed somewhere else, already almost forgotten. It always has. It always will, for tonight, and it will still be holding, quietly, patiently, when you wake.